Hey Ramblers, congratulations on finishing the first quarter. You've really set the foundation for your continued work in this geometry class. We're going to use the theorems and definitions that we've learned for the rest of the year, but they won't come in such a sudden rush as they do in the first quarter. So things tend to spread out a little more evenly, and if you feel as though the class is beginning to make sense, then you're in really good shape because things just kind of build incrementally from here on. We're going to get into some proofs called detour proofs, and they're really no different than what we've been doing. They're just a little more complex. In fact, some of the proofs we've done already have been detour proofs. So there really isn't any new structure. I'm just going to point out where the detours are in a couple of the first examples that we look at today. The real trick at this point is to start planning a strategy. So maybe when you look at the givens and what you have to prove, instead of just proving right away, maybe take a step back and look at what you have to prove and work backwards. So I hope you enjoy the video. I hope it helps. And take some time to pause and really figure out a strategy as we go through some of these examples. Okay, good luck. All right, let's take a look at this example as our introduction to detour proofs. We're told that BC is congruent to CD. So let's go ahead and mark that. We're told that CG is congruent to CF. Oops. And we're told that angle AGB here is congruent to angle DFE or EFD. All right, from that, they want us to prove that AG is congruent to FE. Now, AG is part of one of two different triangles, as is FE. So we should take a step back and look at our strategy. How are we going to handle this? Well, are we going to prove that the big triangle AGC is congruent to the big triangle EFC? Or are we going to work on these smaller triangles on the outer edge? Triangle EBG congruent to triangle EDF. All right, well, knowing what we're given here, we can easily pick up the angles here at C for vertical angles and prove that triangle BGC is congruent to triangle DFC. And so that's going to be our first detour. Now, as you can see, the green triangles corresponding with the green text for the proof don't give us AG and FE congruent, but we are able to pick up some corresponding parts from these two green triangles that will help us prove that triangle ABG is congruent to EDF. So let's take a look now at the rest of the proof. Okay, I've written in red the corresponding parts that we picked up from the green triangles because that's essentially what a detour proof is. It's a proof of some triangles in order to pick up some additional corresponding parts. So we see that angle CBG is congruent to angle CDF from CPCTC, and that gives us that angle ABG is congruent to angle EDF because subs of congruent angles are congruent. Then it follows that side BG is congruent to side FD. And so now we can see that since angle AGB is congruent to EFD from the givens, that the triangles ABG is congruent to EDF by angle side angle. So now we have the triangles that we want, these beige triangles. And AG is congruent to EF because corresponding parts of congruent triangles are congruent. All right, so that's a detour proof. First we had to prove the green triangles in order to pick up the corresponding parts that I've written in red. And then we get the triangles that we really needed to prove because AG and FE were part of those triangles. All right, we'll look at another example from the homework, and then you could be trying some on your own tomorrow in class. Number 16 in the exercises for chapter 4.1 provides another example of a detour proof. Here we see that AB is congruent to AC, and that BD bisects the base angles, and CD bisects the other base angle. So we know enough about isosceles triangles, or the theorem that if sides are congruent, then angles are congruent, to recognize that all four of these angles here at the base are going to be congruent. Alright, so what should our strategy be? Well, we recognize that if we're trying to prove that AE bisects BC, then we're going to have to prove that BE is congruent to EC. Well, BE and EC are part of which triangles? Take a minute, hit the pause button, and work out a strategy. Try to work backwards from what you have to prove to what you're given. Alright, my proof strategy is showing that either triangle ABE, the large triangle on the left, is congruent to ACE, the large triangle on the right, or proving that the smaller triangle DBE on the left is congruent to the smaller triangle DCE on the right. Let's take a look at what we're given and see if we can kind of figure out which is the best route to take. Now, since this triangle is isosceles, we know that this angle down here at B is congruent to the large angle at C. And so that makes it look like, we're in good shape. We have a side and an angle, and so if we could just get BE congruent to CE, we'd have side angle side. But wait a minute, if we knew BE was congruent to EC, or if we could show it, we wouldn't need to prove the triangles at all, because that would be what we're supposed to prove. So that can't be it. Is there any way then to get the angle up here, angle BAD, congruent to angle CAD? Well, all the given information points us down to the base angles. So let's try and prove triangle ABD congruent to triangle ACD and pick up some corresponding parts. Alright, so here's my proof. I first started out with AB congruent to AC, and then angle ABC congruent to angle ACB. We take the two givens, that the BD and CD are bisectors, and that means that angle ABD is congruent to angle ACD. So ABD is congruent to angle ACD. Well, then the smaller angle, DBE, is congruent to DCE. So therefore, DB is congruent to DC, because if angles are congruent, then sides are congruent. So that allows us to show that these green triangles, ABD is congruent to ACD. Now, that lets us pick up the corresponding part of angle ADB congruent to angle ADC. Now, that's useful to us because by supplements of congruent angles, I can show that angle BDE is congruent to angle CDE, which allows me, by the reflexive property, to prove that DE is congruent to itself. So the beige triangles, DBE is congruent to triangle DCE by side angle side. Therefore, the side BE is congruent to the side CE by CPCTC. So therefore, AE does bisect BC. Now, that's not the only way you could have proven this to be true. We could have just gone after the vertex angle after we proved that the green triangles were congruent. We could have shown that the angle BAE is congruent to angle CAE by CPCTC, and that would have given us the large triangles congruent by angle side angle. So with a lot of these more complex proofs, there's more than one way to do it. But the important thing is that you start to develop a strategy, figure out which pieces you need to prove the triangles you ultimately need, and then moving forward. It's not as easy as it used to be, but with a little practice and strategizing, you should have a lot of success. Okay, I hope this helps, and thanks for watching.